This is part 3 of building the scoreboard. Problems. With a project this big, you can expect anything that can go wrong usually will. And I am no exception to that one. Anything that could have possibly went wrong has went wrong. Although a few things went right, but a lot of things went wrong. Anyway, the processor board laid out just nicely. Got a big monstrosity under there, but everything's just fine. It's powered by your standard ATX power supply. There's the rest of the parts I have to put in. Anyway, about what went wrong. First things first. The Series 2 XB module. And anybody that's familiar with XB that has played the Series 2 and have had a lot of problems with it, I am no exception. I've had nothing but trouble out of this Series 2 module. If you may or may not be familiar with XB, it is an 802.15.4 radio, which I think Bluetooth is 802.15, but this is kind of like it's a Zigbee extension off of Bluetooth. Anyway, the module has dedicated programmable I/O pins. You can program the XB module to set the pins to be as an input, output, sample times, and etc. alongside of a UART. Okay, well, I had the UART thing working properly, but I could not get the I/O pins to get to toggle to be able to reset the microcontroller for boot mode. I tried my hardest. Then it got to the point where I had to reprogram the radio at least 5 times before it would even link up again. Because every time I would read the configuration off the radio, even if I just read it, maybe changed one thing and programmed it, it'd break the link. They would not talk to each other anymore. And I never understood why. Because the destination address between both of them were connected to each other. So they should link right up, but they were not. They're running the ZNet 2.5 firmware. That's the only one I can actually even get to link. It's point to point. So when I finally got them to link up again, I just said, heck with it. I'm not even going to bother with the I/O pins. So what I did was I modified the program code to send an S character. The S character puts it into boot mode. So that's pretty much the same thing. But if the processor ever halts, you're screwed. Okay. The next problem I ran into, and this is a much more critical problem. I originally, with this design here, if you look at this design here, you've got these IRL IZ14 MOSFETs. These are logic level FETs. The gates saturate at 5 volts. They're N-type, N-channel. And the reason why I went this way is for setting the color, because they're going to set a huge group of LEDs. Because if you look, the type of LEDs that I'm using are common anode, meaning your supply power is here. You ground this side for red, or you ground this side for green. No problem, right? Well, there's the LED. I decided to use one of the LEDs right here. And I noticed a problem. The LEDs that came in were common cathode LEDs, which totally blew away my design, because the center pin has to be grounded, and you give this a positive voltage to go to red, or this a positive voltage to go to green, and the voltage drop between these two LEDs are completely different. The red has got a 1.9 volt drop at 10 milliamps. This one has a 2.4 volt drop at 20 milliamps. Huge difference. So my PWM design is not going to work. I'm going to have to do 2 things. One, the source transistor will be taken off. So there's a 330 ohm dropping resistor. And that's another thing. I'm going to have to put dropping resistors on each one of these LEDs. That's roughly 1,000 and something dropping resistors. That's a lot of dropping resistors. resistors. Luckily it was only $20 in resistors, but still, that's $20 extra in the budget that I didn't have. So, needless to say, the boss is not happy. But hey, I can't help that China sends you the wrong LED types. Or I may have not paid enough attention. But regardless, the original transistors that were going to be used for my sync transistors, the IRL IZ14s, are insulated packages. And they're N channel. But since now, instead of syncing a mass current from all the LEDs, I have to source a mass current of all the LEDs. So this transistor has to go bye-bye, because they're going to start, these are going to sync instead of source now, because this is now a sync pin instead of a source pin. And that also means the MOSFETs can no longer sync, they have to source current. So I had to use the same topology, except this is the MOSFET instead of a PNP transistor. And I had to use a P-channel MOSFET right here. And I had to come up with this monstrosity with an isolator to isolate the collector point, which these metal cases are tied to the collector. Or, well, not the collector, I'm sorry. The source, or no. Gate, source, drain. No, gate, drain, source. I'm all confused. They're hooked up to the drain. Meaning, on a P-type MOSFET, the drain is actually your output to source the current to the LEDs. Your source pin is tied to your positive voltage, and your gate is hooked up to your drive signal. Now, since P channels, you have to ground the gate for them to turn on, or the gate has to fall below the source voltage because it works in the reverse direction. I got to have the N-type transistors, so a logical high turns these transistors on and drops the voltage on the gate, which turns these transistors on. These are IRF 9540s. I hope this works, because I tested it in an online Java circuit simulator. I can only get a maximum of 1.09 amps, even short circuit current. But it could be the simulator as well, not simulating the MOSFET correctly, because I know if I turn this gate on and I do a short circuit on 12 volts, these transistors are going to explode. I already know that. They're going to get so hot they'll explode. So I need 11 amps if all the LEDs are turned on. I need 6 amps on the red, and I need 11 amps on the green. Because this is your home red, home green, guest red, guest green, time red, time green, downs red, downs green, yards to go red, and yards to go green. Downs, I'll probably never change the color on. I'm not sure. But if these both can turn on and give you orange. But so I averted that crisis. But I'm still not out of the woods yet. Let me grab me a power cord so I can plug this guy in. Okay, power's off. Go ahead and plug in the cord. If I can get it to plug in here. These are the LEDs. I've only got one dropping resistor of 470 ohms on here between the two LEDs, which is not really enough. The green needs to be about 560, and this is only 5 volts and not 12 volts. But still, though, I just hope, because this is an outdoor scoreboard, I just hope these LEDs are going to be bright enough, because that's all bright that LED gets. But again, I'm using a 470 ohm dropping resistor at 5 volts, so the current's a little low, maybe about 12 milliamps through the LED. I haven't actually calculated it, but that's basically what I'm getting. That's all as bright as it gets. And this is just fluorescent lighting in the room. I really hope this is going to work out, because that's $205 in LEDs. And my job if I don't get this correct. Anyway, so this works on your standard ATX power supply control. You got your standby 5 volts. This is a transistor that grounds this wire, which is hooked up to the green wire, turns the power supply on, There's also a feedback pin. I think it's this purple one right here. Bluish purple. On the camera it looks blue, but it's actually purple. Which is a signal source pin that tells the microcontroller that the power supply has successfully turned on. The board is slightly warped. These were really warped when I got them. I had to take the heat gun and flatten them out. So I can successfully move on from this because now I got to start building the LED segment drivers, and then I've got another big board to build the marquee driver. So that's it for part 3. Stay tuned for part 4.